Hello, everyone, and thank you for joining us for our webinar, Monitoring Thermal Phase Transitions with Viscosity. Evaluating thermal transitions of polymers and proteins is important for establishing the structure-property relationship for the macromolecules under various relevant conditions. For example, this valuable information can be used to select the most appropriate thermo-responsive polymer formulation for common applications such as bioinks, drug delivery systems, or food stabilization. Today, we will discuss the use of our VROC technology to probe the temperature-dependent viscosity of polymers and proteins during heating-cooling cycles to identify thermal phase transitions and denaturation. Today's webinar will be hosted by Dr. Sohelia Shabani and Dr. Stacy Elliott. Dr. Shabani obtained her PhD in mechanical engineering at Iowa State University and has been working on microrheology of hydrogels and functional materials. Dr. Elliott obtained her extensive experience and rheological knowledge through her education at Carnegie Mellon University in Princeton, as well as her experience at both Alcon and DuPont. Without further ado, I turn it over to you, Stacy and Soha.
Okay, hi everyone. Welcome to our webinar today. I'm Soha, and today I'm here with my colleague Dr. Stacy Elliott, and we're going to talk to you about monitoring thermal transitions in polymers and proteins with viscosity. I'm going to start off this webinar giving you some quick background about thermal transitions in polymers and proteins, so you will learn about the importance and applications of them and the nature of the experiments we have done. Temperature variation can induce reversible or irreversible microstructural changes in complex fluids. Thermo-responsive polymers such as gelatin, carrageenan, and chitosan undergo reversible changes in material state or phase transitions. These polymers can form gel during a cooling or heating cycle. The thermomodulation property of polymers makes them an ideal candidate for a wide range of applications. For example, hydrogens that can form gel at 73 degrees Celsius or body temperature are suitable drug carrier for drug delivery or wound healing applications. These hydrogens are liquid at room temperature but become gel at a physiological temperature or above that temperature. They can remain on site for a long time and improve drug absorption. On the other hand, polymers that can form gel upon a cooling cycle are good candidates for 3D printing applications, so that prior the deposition or extrusion, polymer is in liquid state, but after deposition on a cooling platform, as temperature drops, they can form gel and become solid. Unlike the polymers, proteins or antibodies undergo irreversible changes in a structure when heated above melting temperature. So that heat increases the kinetic energy and causes the molecules to vibrate more rapidly. This vibration can disrupt the hydrogen bonds, hydrophobic interactions, as well as van der Waals forces, causing the unfolding of proteins' 3D structure. So the protein is eventually denatured due to loss of its structure. So evaluating thermal transitions of polymers and proteins is important for establishing the structure property relationship. For example, this information allows us to select the most appropriate thermo-responsive polymer formulation for common applications that I mentioned, such as bioinks and drug delivery systems. In pharmaceutical applications involving proteins or antibodies, denaturation is an indicator of stability. So knowing the denaturation temperature, you can optimize conditions that enhance protein stability. In this webinar, we will show you how we use our VROC technology to detect the thermal phase transition in polymers and denaturation in protein during heating or cooling cycles. Although thermal transitions can be monitored with techniques such as dynamic light scattering, viscosity is an alternative due to its sensitivity to minor changes in the fluid microstructure. And our VROC technology is so sensitive and can nicely detect minor changes in the fluid structure. With that in mind, I want to talk to you a little bit about our technology that we use for measuring viscosity. Since we have had a full review of our technology in our previous webinars, I'm just gonna go over a quick overview of this technology. Our technology is called VROC technology, viscometer rheometer on a chip. That is basically a combination of microfluidics and MEMS, or microelectromechanical systems. So we have a rectangular microfluidic channel where we have 4 pressure sensors that are located along the base of the channel, and they can measure pressure drop as the fluid flows through the channel. We control the flow rate, or Q, through the channel, and we can monitor pressure drop as the fluid flows across the pressure sensors. Since we know the geometry of the channel, we can calculate shear rate from the flow rate and the dimensions of the channel, or width and depth of the channel. And knowing the pressure drop and dimensions of the channel, we can then calculate shear stress. And shear stress divided by shear rate gives you viscosity. This is how we calculate viscosity. So we can control shear rate, measure shear stress, and calculate viscosity. For today's experiment, we used our fully automated and high throughput viscometer, which is VROC Initium 1 Plus, that allows us to monitor temperature dependent viscosity during a heating or cooling cycle. For our first set of experiments, we looked at the viscosity changes of carrageenan hydrogel as a function of temperature. Carrageenan is an important class of polysaccharides that shows an interesting thermo-reversible gelation behavior upon cooling the solution. In addition, the presence of Cantor ions, such as potassium ions, can promote gelation of carrageenan in aqueous solution, and it can shift its gelation temperature. So in this webinar, we will show you how ionic strengths and the presence of salt can affect thermal phase transition and gelation temperature of this material. The goal that we have is to show how we use our VROC technology and viscosity measurements to detect thermal phase transitions. So we made 3 samples. The first sample was prepared by dissolving carrageenan in DI water. To study the effect of ionic strengths on gelation, we prepared 2 samples in KCl, or potassium chloride solution, instead of DI water. So 0.5 weight% carrageenan was prepared by dissolving carrageenan powder in 0.1 and 0.2 weight% KCl solutions. We measured viscosity with the VROC Initium 1 Plus using an A05 chip, and we made a protocol for a cooling temperature sweep experiment. Temperature sweeps were performed starting at 60 degrees Celsius down to 4 degrees Celsius. However, in the Initium, the temperature can be set in the range of 4 degrees C to 70 degrees C. Before I move on to the next slide, I just want to emphasize one of the interesting features of VROC technology. Our VROC technology is a closed system, so the fluid flows in a closed channel that eliminates the presence of an air-fluid interface, which you have in cone and plate rotational instrument. So you're not going to have issues with evaporation. Also, migration to the interface and basically formation of locally high concentration interface is not an issue here, and this won't happen in our system because of the closed design and the lack of air fluid interface. So there will be no artifacts due to interfacial viscosity contribution. Actually, running rheological measurements at high temperature, say 70 degrees C, would be challenging in any sort of rheometer. However, you can be confident what you measure with our system is the bulk viscosity and not containing the artifacts due to the interfacial effects or evaporation. After this quick review of instrumentation and sample preparation, I'm going to go over the viscosity data I collected from our VROC Initium and share some results with you. This figure shows changes in the average viscosity as a function of temperature under a constant shear rate of 100 inverse second for solution of 0.5 weight percent carrageenan in DI water. This sample was cooled from 40 degrees C to 4 degrees C. Based on data from this figure, as the temperature decreases, a sharp increase in viscosity is observed at around 15 degrees C. That indicates the gel formation or salt-gel transition. Now we plot the sample that was prepared in 0.1% KCl that allows us to understand the effect of ionic strength on thermal phase transition. We can see that the sharp change in the viscosity for this sample shifted to a slightly higher temperature, where the viscosity increases from 20 millipascal second at 21 degrees C to around 48 millipascal second at 18 degrees C. So definitely we have gel structure at 18 degrees Celsius. However, for the sample without salt, gel is formed at a slightly lower temperature. The next plot is for the sample that was prepared in 0.2% KCl. So it means that we have higher concentration of salt in the solution. So we increased ionic strength to see how it affects the transition. This sample shows a higher salt-gel transition or gelation onset and exhibits salt behavior at 40 degrees Celsius and gel formation at 33 degrees Celsius. In addition, viscosity for this sample, as you see, continued to increase after the salt-gel transition during further cooling. However, the first two samples plateau after the transition. It is well known that generally the gelation of carrageenan is composed of two steps that involves the formation of double helices upon cooling or the transition from coil to helix structure, followed by aggregation of helical chains and formation of three-dimensional networks. On the other hand, the presence of salt, such as KCl, is an effective way in promoting gelation and aggregation of helical chains due to interaction between cations and sulfate groups in the crystal structure of carrageenan. With that in mind, here I'm going to show you the effect of shear rate on the temperature-dependent viscosity and salt-gel transition of the sample that contains 0.5 weight percent carrageenan in 0.2% KCl. It is clear from the results that with the increase in shear rate from 100 inverse second to about 2900 inverse second, the viscosity decreases. That shows the shear thinning behavior of carrageenan. As you see, the sharp increase in viscosity, that is an indication of salt-gel transition, is observed in both cases. However, the increase in viscosity during the salt-gel transition at high shear rate, I mean 2900 inverse second, becomes less pronounced, which likely indicates that hydrodynamic forces at high shear rates can disrupt gel structure and it can limit large network ordering. Okay, that was sort of quick overview of thermal transition in carrageenan hydrogel, and now I'm gonna turn it over to my colleague Dr. Elliott, and she's gonna go over some details about thermal transition in Poloxomers and proteins and start sharing some data with you.
Okay, thank you, Soha. Okay, so now we're going to move on to a slightly different system. So Soha had explained the carrageenan and how the sol-gel transition comes from this behavior of the molecules going from a coil type structure to forming helical structures that can then aggregate with neighboring molecules, which can be enhanced by the salt. So this is our next molecule that we're going to talk about is also thermo-responsive, but has a different mechanism. And the molecules we're talking about here are Poloxomers, or you might know them by some other trade names depending on where you obtain them. But what these are, they're all tri-block copolymers consisting of ethylene oxide groups and propylene oxide groups, and they have an amphiphilic nature, meaning that they have these different groups have different levels of hydrophilicity or hydrophobicity, whichever way you want to look at it. So the mid blocks, the polypropylene oxide blocks, are more hydrophobic than the end blocks, the PEO, because of the presence of this extra methyl group. So because of this amphiphilic nature and the fact that the mid block is more hydrophobic, these will self-assemble to various degrees in aqueous formulations. Now this self-assembly is going to depend on the concentration and the temperature. In fact, this is what drives the properties of the molecule. And unlike when we get to the proteins, the denaturation, this is reversible, just like the carrageenan. So the self-assembly here, if you're driving it due to concentration or temperature, this can be reversed, and we'll illustrate that with respect to temperature. Now these poloxomers come in various forms. Mainly what's varied is the molecular weight of each block, and the specific type of self-assembly that you'll get will depend on these molecular weights, and particularly the ratio. So the overall molecular weight and then also the ratio. Now the polymers that, or the poloxomers that we're going to talk about, the general behavior that we have is that at lower concentrations or lower temperatures, depending on what you're really using to drive your transition, you start off with the individual molecules. And then as you increase concentration or increase temperature, you'll then drive these molecules to form spherical micelles, where this hydrophobic mid-block, the PPO, will then isolate itself in the core of the micelle. And then finally, at the highest extremes of your conditions, then you'll have entirely or predominantly micelle structures. And generally, these are used for rheology modifiers, solubilizers. They can inhibit sedimentation mainly because of the bump in viscosity that they provide. And these two, like some of the other materials that we've talked about, can be mixed with supportive polymers as well. So it's not uncommon for these to be mixed, for example, with the capocarrageenan that Soha was just describing. Okay, so let's take a look at the behavior of these. So now we're going to look at the relative viscosity as a function of temperature. And we're going to look at two different types of these poloxomers. They're going to differ in both overall molecular weight, one of these being the P188 being slightly lower on the molecular weight than the P407. And then there's going to be a difference between the ratio of the blocks. And the way we did this testing initially was we did the heating cooling cycles where we ramped up first in temperature and then cooled it back down. And we did initially just automatic mode, where automatic mode for our automated viscometer is basically adjusting the flow rate or shear rate to try to keep us in the mid-range of the % full scale pressure. So it's kind of like a ideal flow rate for that particular sample. But we will, as you'll see, address the shear rate dependence of these molecules in solution in the next few slides, which, as you saw when when Soha was discussing the capocarrageenan, it's quite important to the response of the material, the shear rate. But let's just start with the temperature dependence first and what we're going to learn from that. So on the top plot, we have relative viscosity as a function of temperature. Relative viscosity is just the viscosity of the solution at any given temperature divided by the viscosity of water, which is what these are dissolved in at each of those temperatures. This is just how we define the relative viscosity. And we have both of these types of poloxomers in the DI water at different concentrations. And first of all, I just wanted to point out that although maybe in some cases it's not so obvious, we do have two curves here overlaying. One is the heating curve, one is the cooling curve. And you can see that this process is fully reversible. So we always get back to where we started in terms of viscosity value. Not unexpected, we see that as we increase the concentration of our polymer, that we see an increase in the relative viscosity. Now, and this is true for both types of Poloxomer systems, the full reversibility and the increase in viscosity as we increase concentration. So now one of the things I want to point out is, obviously we have some very highly non-areneous behavior here, and slightly different than what we saw with Soha's carrageenan samples, where we saw basically one sharp transition as she cooled down the sample, that sharp transition where she jumped from a lower viscosity to a higher value, and perhaps something that was even in the gel state. Now we see this peak in viscosity. Now we have the peak in both of the Poloxomers, although it is shifted depending on the type of Poloxomer that we have. So one of these is in the vicinity of what would be body temperature, so somewhere around 37, which is actually a common application for this type of Poloxomer, where you try to perhaps introduce this into the body with the hopes that it will increase in viscosity or gel and promote the controlled release of different drug products. So this is distinct from the transitions temperatures that we see in the P188, which is shifted by about 30 degrees at about 65 or so. So this is quite distinct from the way the carrageenan looked. And so if we were to construct a very generic phase diagram of how the Poloxomers look, as we look at temperature as a function of concentration, we would expect that in certain regions of this phase diagram, we're going to see two transition temperatures rather than the one that we were identifying with the carrageenan samples. So let's think about how we can identify what part of the phase diagram we're in by doing some more detailed experiments. So what we're going to look at then is what you'll notice. Let's focus on the P407. What you'll notice is that in this peak region for the lower concentrations of the Poloxomer, we have very reproducible data and no issues, getting consistent, the same response here. I'll just point out, I have not yet, but any error bars here, all data points have error bars, and they're all 3 times the standard deviation, or 3 sigma. So what we'll see though is that once we get into this 15% concentration of the Poloxomer, the P407, we start seeing this very more erratic behavior. It's more inconsistent. It's harder to get consistent data. So let's sort of probe in more detail with viscosity as a function of shear rate to understand what might be happening at these different concentrations in this peak zone and what that might mean in terms of where we are in the phase diagram. Okay, so let's start with the 14% Poloxomer. And again, we're going to combine the shear rate and temperature sweeps. So this is an easy thing to do on the initium. We can program all of this to do on the single sample volume that we loaded. So we're going to look at then distinct temperatures on our profile here, our temperature profile. And we're going to conduct as broad of a range of shear rates as we can at each of these temperatures. And so that's what we have on the plot on the right. So now we're looking at each of these temperatures that I've identified with an arrow. We're looking at a broad range of shear rates. So what we can see is that when we start off at 20 C, we're starting off with a material that is Newtonian or independent of shear rate. And as we ramp up the viscosity and approach this maximum in our viscosity versus temperature, we start seeing the onset of non-Newtonian behavior. And this continues then as we go down on the opposite end of the peak here, and then we return to Newtonian behavior at 70 C. So, and then the final thing that I'll kind of point out with these plots is that we see that the non-Newtonian profiles, they all sort of come together as we get into higher and higher shear rates. So similar to Soha's samples, you're going to see, if you're just doing a viscosity as a function of temperature, you're going to have a very different response depending on which shear rate you choose. So you're going to see the maximum difference and really emphasize the peak when you're down at the lower shear rates here, but then this will become minimal as you go to the higher shear rates. Another thing I wanted to point out is that we have all of these flow profiles with respect to shear rates have a very nice, well-defined low shear viscosity plateau with the onset of shear thinning. So these look more as if we're just, as we ramp up the temperature, we're changing the properties, but we're not going deep into that gel state because we're not seeing any indications of yielding, which you would expect for a gel the general thought is that when you have this gel, you're seeing some sort of solid-like behavior, at least at low stress. So, and just to sort of, again, if we think back before I move on to how we're going to look at some of the higher concentrated samples and identify what part of the phase diagram we're in there, I just wanted to comment. So if you think back to a couple slides ago, when I was sort of laying out how these form micelle structures, we can kind of understand how this behavior comes from changes in those micelle structures as a function of temperature. So, and again, also thinking about the nature of the polymers that are part of the Poloxomer. So as we increase the temperature, what tends to happen in these PEO, PPO systems is that initially you start seeing some sort of swelling of this polyethylene oxide sort of corona on the micelle. And then ultimately, as you keep increasing the temperature, because what tends to happen in these aqueous systems as you go higher and higher in temperature is you lose some of the hydrogen bonding, which really enhances the solubility of these molecules. So then these micelles then can start to collapse somewhat more. And so then we see a drop in the viscosity. So we're seeing something sort of a swelling with temperature and then a drop in viscosity coming from those molecules then starting to collapse and become more condensed. So this can be kind of a general way of viewing what is happening with the structure to give rise to the types of viscosity behavior. So now let's take a look at our higher concentration of the P407. And so again, I mentioned that when we get into the peak zone, we start seeing a different type of behavior here. We still have the peak, however, we have trouble when we were working in the automatic mode in getting reproducible data. So we have these much larger error bars. And so let's now look at shear rate sweeps at these three distinct temperatures. One as we're sort of entering the peak, one as we're in the midst of the peak, and then one as we're exiting, to see what type of behavior here, what the shear rate dependent behavior here looks like, and what that can tell us about the phase transition or where on the phase diagram we might be. So if we look at sort of the endpoints here, the 30 and 50 degrees C, we can see that we have nice, well-defined low shear plateau viscosities and then the onset of shear thinning. So this is very similar to what we were seeing with the lower concentration P407. But now when we're in this peak zone here at the maximum, close to the maximum at about 40 C, we have a very different type of behavior when it comes to our viscosity as a function of shear rate. Now we start seeing this the absence of a very clear low shear plateau viscosity at the earlier shear rates. So I just wanted to kind of point out something that maybe it's not obvious, but we'll look at it a little more closely on the next slide, is that we do see this power law behavior at the lower shear rates at the 40 degrees C. So viscosity is dependent on the shear rate in a power law type manner. And if you look at this a little more closely, what you'll see is the slope of this decay in viscosity as a function of shear rate is close to -1. So that means that N here is approaching 0. Why that's significant and why I bring it up is that if we have a power law response in the viscosity, that means our shear stress will depend, will be basically scale on the shear rate to the N power. So if N is going to 0, that means the shear stress is independent of shear rate. And that's actually a red flag when you're doing rheology experiments because, physically that's not something that would make sense unless, if that would not make sense if you have a nice well-defined flow field and a uniform sample. But if something is happening to, change the nature of the sample as you're shearing it, making it perhaps inhomogeneous in some manner, then this is kind of a red flag and we want to probe this a little more deeply. Okay, so let's talk about this stress then. So we're going to look at shear stress, both in terms of transient behavior and stress as a function of shear rate. And we're looking at, just to show, to sort of contrast, we're going to look at both of these at the 30 C and then at the 40 C where we're in this peak zone. So at the 30C, where we have the nice, well-defined low shear plateau in the viscosity, our transient curve is, very rapidly hits a plateau and stays on the plateau. Nothing unusual here. This is typically what we see as we start pumping the fluid and we have a well-defined flow field. However, if you look at what's happening at 40C, we see this overshoot in the stress, which then decays, and then we see maybe a slight gradual increase with the stress as we keep pumping the fluid. So this overshoot in the stress is kind of another indicator that we might potentially be having something that is yielding. So what happens is, as you start flowing the sample, you have to have additional stress response to basically force this fluid to start flowing near the wall of the flow channel. So this is one thing that's indicating that perhaps for this 15% P4O7, we're more into this gel structure, where we, at a particular concentration, as we increase temperature, we go through the gel phase before we then move back into a sol phase. So another indicator that we have this type of yielding behavior is if we look at stress as a function of shear rate. And again, I have both of these temperatures to show the contrast. So a very typical response where everything is, flowing nicely, no concern about yielding. We have a consistent increase in stress as a function of shear rate, as you would expect at the 30 degrees C. Whereas at the 40C, we have this region where it looks like it's within the error of the experiment. And again, I've included the error bars at 3 times the standard deviation. We see this sort of plateauing of the stress before the stress starts to increase with shear rate. And again, that supports that we're in some sort of state where we're yielding, and this is the rheological response that tends to be the signature of that process. So that's sort of where I'll stop on the Poloxomers. So this is a sort of a complementary type of reversible phase transition, although in this case we have 2 transition temperatures, unlike the carrageenan that Soha talked about, which had the single transition temperature. So now we'll move into a quick discussion on something that is irreversible. So everything that we just talked about now, if you're ramping up the temperature and you do cause it to gel, as you cool it back down, or in the case of the Poloxomers, as you cool it back down, it will go back to its original phase. And in the case of the carrageenan, if you warm it back up, it will then go back to that sol phase. With the proteins, however, when you're dealing with the denaturation of these induced by thermal stress, this is irreversible. So there are certain ways to denature proteins with adding small molecules that, if you can then ultimately remove the presence of those molecules, that type of denaturation is reversible, but the thermally induced is not. That's permanent. So what is the denaturation? As Soha already discussed in the intro, where she had a nice diagram showing the protein molecules or antibodies. This is a loss of higher order structure. So this is loss of any sort of crystalline domains, perhaps, or helical structures that will unfold. And so that's just sort of part of the problem, perhaps, with the denaturation, is the loss of this higher order structure. Sort of another issue that you have to consider is that as the molecule opens, now you have numerous groups that weren't available before to lead to more aggregation. So perhaps, when the molecule was folded, you had hydrophobic domains that were unable to group up with another hydrophobic domain on a neighbor. But once the molecule unfolds, now you have more options perhaps for additional aggregation. So that's what I mean by, the loss of the structure can facilitate further aggregation of these molecules. And so what we can do is we can use the viscosity measurement to identify what is commonly referred to as a melting temperature, which is the point at which this molecule will denature. And you can also, and again, Soha hinted at this when she was giving the overview of our webinar today, you can sort of use this as a probe of stability of the proteins, mainly driven by the environment that they're in. So that would include, changing the buffer composition, either in terms of adjusting pH, which is what we're going to focus on the first discussion here, or perhaps introducing different types of excipients. So with all that sort of intro, let's look at some data that we have. And so this data is with bovine serum albumin, commonly BSA, abbreviated as BSA. We do these experiments for the denaturation of the proteins in the dilute state. If we tried to do the similar experiment in a concentrated protein or antibody solution, and we run a much greater risk of basically forming an irreversible gel in the flow channel that then we would not be able to clean out. So when we do these, we generally do them in the dilute state because there's much less chance of forming an irreversible gel that can't be removed from our flow channel. So BSA has an isoelectric point at about 5. So this is where this molecule has a net charge of 0. And what we're going to look at is the impact of varying pH and seeing how that impacts this transition with temperature. And so we're going to do this by varying buffer. So we have different types of buffer, so that we have a solution in an acetic buffer, which is close to these isoelectric points, so close to net 0 charge. And then we're going to use the citric and some phosphate buffers to increase our pH and make the protein more anionic. So it becomes more charged and it becomes more anionic as we move away from that pH of 5. So we're going to look at viscosity as a function of temperature, and just as a reference, we have a sample buffer formulation so we can see what the Arrhenius behavior looks like over the range of, in this instance, from about 25 to 70 degrees C. So this is just that continuous exponential drop in viscosity with temperature. And we'll see that all of the protein solutions, the BSA solutions, track that behavior initially. So it is higher in viscosity because we do have the presence of these higher molecular weight molecules. BSA in this case, I think, is somewhere near 60 kilodaltons. But ultimately, we get to a temperature where we start seeing deviations from this Arrhenius behavior that we see continuing on in the buffer. And what we also see is the extent of deviation from the Arrhenius behavior varies quite significantly depending on the buffer composition, specifically the pH. So we see that at the pH close to the isoelectric point, we see the biggest and most abrupt deviation from the viscosity. So we see very quickly at a particular temperature, somewhere about 62 or so, we see the viscosity increase quite significantly. Whereas the increase is hardly noticeable on this particular plot for the higher pH solutions or the more charged solutions. So just to think about what might be happening here, as the molecules unfold and we have the potential for more attractive type interactions available, if you have a higher charge on the molecule, this provides an electrostatic repulsion. And so if you're familiar with the concept of the colloidal interactions, this electrostatic repulsion is a stabilizing mechanism. It's a barrier to the attractions that might exist. So if you have something that's more charged, it has more of this electrostatic barrier, it could potentially then be the contributing factor here, that we're preventing the enhanced aggregation because we have some additional charge which provides a barrier to the attraction. So this could be one reason why when we're so close to net 0 charge, that's going to be the point where we have the least electrostatic barrier, and perhaps then this could be leading to our most extreme change in viscosity. So we can also look at this a little differently at the bottom, where we looked at relative viscosity as a function of temperature. And so again, just like as we discussed with the Poloxomers, relative viscosity is the viscosity of the protein solution at each temperature divided by the viscosity of the buffer at that temperature. And so we see the flat profiles as we're heating the sample, which are the filled points, until we get to a particular temperature. And then we see this sort of sharp change. And as we cool it down, what we see is this is indeed irreversible, because we do not return, unlike the Poloxomer, unlike the carrageenan, we do not return to our original viscosity. We return to a viscosity that is higher than what we started out when we get back to 25C. And what we notice is that when we have a lower pH, so this lower pH is closer to the isoelectric point, we have less charge, less stabilization, we see that we have a larger irreversible change in the viscosity than when we do at a higher pH where we have a higher charge on the protein molecules. So here we can see very clearly, we can sort of identify approximately, where is that melting temperature, and then which doesn't really change with the buffer, but what changes with the buffer and with the pH in this case is the extent of that irreversible change. And so we can identify the stability of these molecules under thermal stress dependent on the buffer, particularly the pH of the buffer. And so I'll mention I've sort of heavily focused on the charge stabilization that exists as we move away from the isoelectric point, but I'll also mention that there are some other things to consider in terms of the BSA, because we also know with the BSA that there's different percentages of the molecule that have a helical structure depending on the pH. So that could also play in here. If you have more helical structure to begin with, then there's sort of more to lose as you heat up the molecule and disrupt that structure and open it up. So there's a couple there's a little nuance there. So let's look at one more example before we wrap up. So here we're going to look at a different model protein. So this is bovine gamma globulin, and again we're going to do this at a dilute state. Again, just to emphasize that it's a little risky to do this in the concentrated state. In this case, 20 mg per mil. Bovine gamma globulin could be a little more problematic, so we had to drop that concentration a bit. And what we're going to do here is we're going to do the same type of experiment, but we're going to look at, instead of focusing on the pH, we're going to focus on introducing different types of viscosity reducing excipients in a base buffer of acetate, sodium chloride, and polysorbate 80. So we're going to do the base case, and then we're going to do this base case plus some of these viscosity reducing excipients. And the excipients that we're going to use, before we look at the data, let's just look at the axes here on this plot. We're going to do histidine, 2 forms of histidine, and then also we're going to use imidazole, which is that functional group on the histidine molecule. And then also we're going to use 2 forms of arginine and the guanidine group, which is the functional group on the arginine. Now, we'll point out that when you introduce any of these 6 excipients into a concentrated gamma globulin formulation with this base buffer, the viscosity drops for all of them. Now it drops to different extents, but these are known to be viscosity reducing excipients for protein solutions. So the question is what sort of benefit, if any, might they provide in terms of enhancing stability during the denaturation of the proteins? And so we do the same experiment. We look at relative viscosity as a function of temperature. Again, we heat and we cool. And what we're going to focus on in this comparison is what is this irreversible change in the relative viscosity, which I've indicated with the arrow here. So you can see that sort of hinting that we're going to have differences where this histidine change between the heating and cooling cycles is significantly smaller. Oops, sorry about that. Is significantly smaller than what we see in the arginine. Okay, so let's sort of summarize the behavior where we have buffer only. So this is the buffer, this is the change in relative viscosity in percentage with the buffer only, and then the corresponding values that we get when we introduce these different excipients into the base buffer. So what we see is there are certain instances, in fact, more often than not, or maybe they're balanced kind of. So about half of these actually we show a loss of stability with their presence, whereas through about 3 of them we see significant benefit in terms of the change in relative viscosity as we denature this particular protein. So this is somewhat interesting because you'd think that if they provide benefits in terms of viscosity reduction at concentrated state, that they might be beneficial also in preventing significant aggregation during the denaturation process. But what I'll kind of point out is that one thing we know different between histidine and arginine, sorry, I keep hitting the pad here on the computer. The difference between histidine and arginine is that arginine is going to have more charge in the pH of this buffer than the histidine. So in that case, and particularly then when we have the HCl molecules attached or associating with these individual amino acids, they're basically acting in a sense kind of like a salt or counter ion to which then can screen the hydrostatic interactions, which can act as a stabilizing effect. So the histidine and imidazole, where this is going to be the least charge, no extra counter ions from HCl, it's going to have the least impact in terms of screening those electrostatic repulsions which act to stabilize. So perhaps that's what's happening here, is you get sort of a negative benefit because you're screening the electrostatics that might be helping you from, the enhanced aggregation that can occur as the protein unfolds. So with that, I'll quickly recap and say that, we found that, using our particular technology, the VROC technology, specifically with the automated Initium 1+, we can really handle easily the broad range of temperatures that you need to look at these thermal phase transitions without any concerns of any sort of interface interfering with your measurement. And we've identified the ability to use this in both reversible transitions like the kappa carrageenan or the irreversible transitions that we see with the denaturation of the proteins. So I'll stop there, and then we'll be happy to answer any questions that may have come up during the presentation. Okay, so we do have some questions. So let me read them out and then we'll answer. So for the Poloxomer samples, did you use the same chip for the relative viscosity versus shear rate study? To do that broad range of shear rates for the viscosity, I actually ended up using 2 chips. So I used our B05 and our E02, and then I combined the data. So oftentimes, if you want to do a very broad range of shear rates, that's what we do internally, is we combine data from multiple chips, and that is in fact what I did there with that. And then secondly, next question, if not, do you mind sharing which chips were used for the Poloxomer experiments? Okay, so that's just a follow-up of the first one there. So we did use the B05 and E02, and sometimes we'll actually need, depending on the exact max pressure of the individual chips, we might actually do some C05 data to sort of bridge those. So if you're not familiar with our technology, we generally have codes for our chips. So if you remember, Soha was initially talking about the A05, which she used for the carrageenan. So the letter corresponds to the pressure range. So as we move through the alphabet, we can achieve higher pressures. So each chip can go to higher pressures than A. And then that number, the numerical value, corresponds to our channel depth. So 0.5 is a 50 micron channel, 0.2 is a 20 micron channel. And so to get to the highest rates, we tend to need to use something like an E02, which has sensors that can handle higher pressures and then also narrower channels, both of those allowing us to get to the higher rates that we were able to achieve. So thanks for those questions. While we wait and see if there's anything else that might come in, I'll mention that don't be shy. Please ask questions. Although if you happen to think of a question later, the way our webinars work are if you have not, if you signed up for a webinar, what we'll do within a week or so is send out to you a link to the webinar so that you could take a look at it again. And if you have questions that come to you later, then we'll be happy to, please contact us and we'll answer those in the future. Okay, so we did have another question that comes in. I know you focused on thermal stability. If you run at high shear rates, do you see viscous heating also impacting the studies, and would that contribute to the results of the thermal study? So you can have viscous heating, but that isn't really relevant in the experiments we were doing here. Generally, that's going to happen if you're getting to very high rates on a higher viscosity material. So we were going to high rates, but not quite high enough to achieve these types of situations where we would have viscous heating. And also because we have such extreme thinning of these materials, because there's just the physical associations that are occurring, we did not have any issues with this type of experiment with that type of phenomenon. We do talk about, I can't remember the date for the webinar, but there was a previous webinar we gave, I think it was in 2021, where we talked about some sort of artifacts in viscosity measurements, viscous heating being one of them, because that will generally give you an artificial shear thinning type response. And we talked about sort of the dimensionless groups that you can use to use the properties of your fluid and then the properties associated with, or parameters associated with your experiment to sort of identify it if that could be an issue for you there. So you might want to dig that one up. So that's viscosity artifacts, and viscous heating was one of the ones we discussed amongst others. So we'll wait one more moment here, and I'll just say that we do give monthly webinars, and we will be, okay, so we did get one more question. Okay, so when we talk about shear rates, are we referring to shear rates in the chip or in the syringe? So we're talking about viscosity in the chip. So I'm just gonna, hopefully you can still see the presentation. I'm gonna go back to one of the first slides that Soha went over. And when we talk about shear rate, we're talking about shear rate in the chip, because this is the relevant one to our viscosity calculation. So just to recap how our technology works, in our rectangular slit flow geometry, we have the pressure sensors spaced across the base of the flow channel. And this pressure drop across the flow channel is how we calculate our stress. And then we calculate the shear rate in the chip using the volumetric flow rate that we are controlling with the syringe pump, and the dimensions of the flow channel. So all the calculations are related to the flow that is occurring in the chip. So the shear rate is in the chip or the flow channel. Okay. So we're coming upon an hour of time. So like I was saying, I'll just say we do have webinars every month, and Eden, our marketing manager, will send out, she's very good at letting everyone know what that's going to be ahead of time, so you can sign up for that as that announcement comes out. So thank you for joining us today, and thank you for your questions, and we hope that you'll join us in August. I guess it's August next month. Okay, thank you.